Okay, so welcome to the first session of this afternoon. The talk's going to be a little different from the introduction that you just heard, but I think nevertheless are going to be fascinating and interesting. I think the focus of this session is on software and some excellent software that hopefully will be useful for you. So first off, we have Carlos from Madrid, who's going to talk about workflows in Scipion. Thank you.
Thank you. Okay, so first thanking the organizers for inviting us to give this talk. And what Scipion is a platform that integrates many different software packages to do image processing in EM. And we are integrating XME, but also EMAN, FreeAlign, Relion, and there are up to 20 packages, more than 200 operations that you can do within Scipion. And it has been mentioned a couple of times, one at the level of streaming processing, at the level when you are acquiring your images in the microscope. So as soon as you start acquiring, we start processing them, and you can early detect problems in your acquisition. And if there is no problem, at the end of your acquisition, you have the early stages of the processing, currently up to 2D classes, you have them already available. So you can go home with the project. And the other one is once you have finished your processing, you could deposit at the EMDB. At the moment, it is not fully ready, but we are working towards that. The whole workflow that you have done so that things are repeatable, people can understand exactly the image processing you have done. So what I will explain today is after acquiring. So once you have acquired, what are the things, the different options that you have? And you could do a very simple processing and you will get a structure, or you can do a more complex processing and you will have a better structure. So actually, I'm the person behind all the mathematics and algorithms behind the algorithms, but I'm happy to make them disappear and only present nice ideas. Okay, so this is a simple processing. So this is a very simplified thing. So you import your movies, micrographs, align them, pre-process, pick your particles, extract your particles, do a little bit of 2D classification, and then construct an initial volume, and you have a final 3D structure. And it is very linear, it is very simple to do, very easy to automate, and you get a reasonable structure. But you don't get the most from your data. If you want to get the most from your data, you have to process in a more complicated way. So Scipion gives you a lot of choices, a lot of programs that you can integrate. You can compare your results with one program to another. You can do consensus things. And at the end, you will have a much better structure. The problem of that is the analysis is more complex. You need to take more decisions than in a straight pipeline. And it is more difficult to automate because of these decisions. So I call this colorless linear image processing, and this is colorful. And the colors are coming from labels that you can put in Scipion. So you can, each one of these boxes is a step you have done, and then you can put labels to your boxes. So that is where the colors are coming from. Okay, so one first warning I would like to make is verify the movie gain. So now I would say most acquisitions are good in the sense that they measure the gain at the beginning of the acquisition and then they measure. But if you keep an old gain for processing your data, then you might have problems with the gain. The gain is drifting over time, so you are correcting with something that doesn't apply to your data. And if you go to Empire, you see that 30% of the Empire depositions have problems with the gain. And there is an algorithm that has been just published on given a movie, estimate the residual gain. And the residual gain should be 1, should be very centered around 1, and very little standard deviation around it. And it is integrated in Scipion. You can put it in the acquisition workflow. You can verify for it. And then the next step would be aligning your movies. And aligning your movies, you may correct for this For the shaking of the grid, that this is all motion core, the old motion core, and XMIP correlation and blur is correcting for this overall global shift. But then there is a domain effect that motion core 2, for instance, is correcting. But even you can go even finer and use a XMIP optical flow that is estimating a shift at every location of the micrographs. And you can go all the way as precise as you want. And if you look at the shifts, for instance, the global shifts, they should look like trajectories normally, or very small cloud of points, but very small shaking. But you shouldn't see strange things in there. And for instance, at the acquisition, we have monitors that monitor these trajectories and discard automatically movies that look strange. They are put aside. The data is never deleted. You can always go back to the data and decide, I will take them in again. But automatically, they don't flow through the pipeline. Then you estimate your CTF. And the CTF, for instance, CTF find 4 and GCTF, they are very accurate in the estimation and very fast in the estimation of the defocus, but they don't estimate the envelope, for instance. And for the envelope, you can use XMIP CTF. We measure a lot of, we have a lot of criteria deciding whether a micrograph is good or not. For instance, this Empire entry is the one of the beta-galactosidase 2.2 angstrom. And 88% of the micrographs were good, but 12%, even in a very good data set, you have micrographs that don't comply with very high quality standards. Here you have a view of how this data set I told you, 2.2 galactosidase, and you see there are many micrographs that have problems at the level of power spectrum. And you have up to 14 parameters to identify all these problems. And also there is one of the boxes automatically checks these parameters and takes decision for you. But you can change the thresholds of all these parameters, etc. Then you pick your particles. You have to choose your particles from the micrographs. And there are many pickers. And in Scipion, I think we have like 10, 12 pickers. And this is an example of how you could combine all these results. So for instance, you can use 3 pickers. One is based on the size of the particles. This one is learning from the user what he's picking. And this one is based on templates. And all of them, a particle picked by any one of them, they are picking about 300,000 particles. But you can go to the other extreme. I only believe a particle is a particle if the 3 of them have found it. And then you have 30,000 particles. And you can stay in between, and you can use more pickers and be very creative about the way to choose your particles. And here is an example. We are using here 2 pickers, one based on the user picking and the other one. So this is learning from the user and then automatically picking the rest of micrographs. And this one is based on size. Particles picked by the 2 of them, you see 5,000, this is a very small data set, and 5,000. If you use a template, you are using GAutomatch, for instance, you are giving perfect templates. And it doesn't mean that using a template will give you perfect picking. So you see that many of them are still incorrect. This one is incorrect, and there are many wrong choices there. So using a template doesn't give you the perfect answer, even if you think, I have given you the perfect thing, so why don't you take that? Because it is a classifier, and all classifiers have false positives, false negatives. And you see, for instance, the particles picked by a template-based algorithm, they are in the same order of magnitude as using 2 different strategies. And if you combine the 3 of them, you're gaining a little bit more, so like 10% more or 20% more of particles. Then normally the way I see people using these things are taking the ore of different pickers. So I believe a particle is a particle if it has been found by anyone. And then probably you end up with many more coordinates than particles. So you have to choose, decide later what is a particle, what is not really a particle. It is simply some background point or in the middle of two particles or etc. So there you can start your 2D processing. So for instance, you have 3 different algorithms. This one is based on very rough features of the particles. This one is based on maximum likelihood. This one is based on vector quantization. And each one has different properties. So I wouldn't use just one algorithm. I would use the failures of one will not be the failures of the other. So applying them in a kind of sequence, like I will get of very bad things, then this one is good also at identifying bad particles. This one is good at identifying good classes and images that are close to those, to the centroids of the classes. And then you can apply a sequence of them. So if this is our basic operator now, we may call it clean 2D, you can apply clean 2D many times. So the output of one clean 2D, you clean it again. And at the end, you go from the 300,000 particles to 62,000. And here is an example at the beginning. This is the 2.2 galactosidase. So this is one of the first classifications. This is the last classification. So you see that you have increased a lot the quality of the particles in your data set. And what happened with the rest of particles? So we had at the beginning many. We have gone down to very few. So what happened with the rejected ones? Now you can take the rejected ones and go again through cleaning. And you can repeat this process. And at the end, you are enriching your original classification from 62 to 100,000 particles. So this is again pointing in the same direction. All these algorithms here, they are classifiers, and classifiers have false positive, false negatives. So a single iteration doesn't give you the full answer of what is a good particle or a bad particle. So you probably want to go from to recover. You have increased this data set, the size, by 60%, 70%. So don't do things only once, and don't use only one algorithm because it has failures, and the failures of one are not the failures of the other. And then you go for your initial volume. So at some moment you will have some classes that you have identified in these steps, and then you construct an initial volume for it. And again, there are many algorithms. And for instance, Eman is proposing from your classes 10 possible initial volumes. Ransack is also proposing 10. Significant is proposing just 1. And then the user typically had to decide, this one is the one I will continue on. But for instance, now you have consensus algorithms that take all these volumes and somehow make them evolve and produce an initial volume for you. And here you have some examples. So these are some of the examples for the beta-galactosidase. And you see, some of them are terribly bad, some of them are good, and many of them are bad. So making a decision here, maybe you do the right decision, it is fine, but maybe you do the wrong decision. So you want an external opinion. This swarm consensus is an external opinion. Take all of them, make them evolve, and at the end you have this one that is a very good initial volume for your refinement. Then typically you go into, once you have an initial volume, you go into a 3D classification step that you may look at it as a pruning operation. So I'm getting rid of all those particles that are still bad after all these filters, and there is still a set of particles that are really bad, but they have survived all these classification steps. And also you may have a discrete heterogeneity, a continuous heterogeneity, and then you're separating your populations. So at the end, you start with your 100,000 particles, you apply your cleaning in 3D or sorting, classification in 3D until you cannot divide anymore. So at some point, these 70,000 particles, if you try to split them into 3 classes, you see that the 3 classes are almost identical, or that one of the classes is taking all the particles and the other 2 are empty. So this is the final point of this pruning in 3D. And this is an example of 3D classification. So if you have a set of particles and you ask the classifier to divide them in 2 classes, you will find these 2 classes. And you may start building a biological story about it. And okay, this is in one conformation, this is another conformation, there is a movement of these domains or whatever. But you should always be careful and put all the check-ins. If you take the particles associated to this structure and go back to the micrographs, you see there are empty particles, broken particles, very bad things. So this is an example of the Einstein from noise. So you have started with a structure, you have given some data set, and it will try to split the data in some way, but it doesn't mean that the split is correct. So always verify all your data. And surprisingly, all these bad particles, they have survived all the 2D cleaning steps that we have put in front. So, and also the 3D cleaning steps. So this is a warning on the quality of the data and all the checks that you should put on your data. Then we can do the same idea. So as in 2D, so you started with 100,000 particles, now you have 70,000. What happened with the 30,000 that have been rejected? Now you can use this operator, that is the cleaning in 3D. You can use this operator and try to analyze this data again and try to repeat or to save a few of them that are still good particles, because there was a wrong decision in the classifier, and in this case you have saved 10,000 particles. And well, now we think we have an homogeneous population. We go to refinement, and you end up with this structure. This is some tutorial data, so it doesn't go to very high resolution. But you have your structure, okay, that's fine. This is my final step. I wouldn't say so. For instance, now you use a different classifier. All these classification data examples that I have been giving to you, they are based on Reliant. Now this one is based on XMIP. And the data used to construct this volume that has, from the Reliant point of view, they are perfectly homogeneous. From the XMIP point of view, they are not homogeneous. And some of it is 2/3, I think, or 3/4 of the data go to the correct structure, but still 1/4 of the data is refined into this thing. So you have data in your data set that doesn't really conform to your structure. So again, use different tools because the failures of one will not be the failures of the other. And then, if you take the 3/4 of the data that are more consistent with your structure, then this was the previous structure. This is the structure with the new with the reduced data set. And you see that in terms of FSC, this is gold standard, so each one of the halves don't see each other. But in terms of FSC, it is better than this one. And qualitatively, you see different features in your structure. So now, again, once you have a structure, it is not your final word on this is the structure that I have seen in the micrographs. Then I'm presenting now one of the boxes that we have recently developed in Scipion. This box is coming from XMIP. This we call it high resolution reconstruction, and it is a kind of auto refinement, projection matching, however you want to call it. with a few ideas. So the first idea is that you should do global alignment until the alignment becomes stable. That makes sense. So you shouldn't take early decisions on what is the angle of your particles. And here we make a lot of, exploit a lot the ideas of significance, statistical significance. I will present a little bit later too. And then once you are sure about your global alignment, now you go into the local alignment. Then you can refine as accurately as you want all the parameters like the focus scale, gray values, angle shifts, whatever. And remove everything that could serve as an anchor for noise. So you try to avoid overfitting. And then also you do this in a multi-resolution. So at the beginning you start doing low resolution reconstructions, and at the end you have high resolution reconstructions. And then this is the significance. So significance is how, let's say you have a number of experimental images, a number of theoretical projections from your volume, and you compute the correlation between your image and the rest of projection directions from the volume. So is this correlation, let's say this is the highest in this row here. So you would assign this angle to this image. But is it really the highest that you could have? So for instance, this projection direction has seen all the experimental images compared to it. So now we can decide this correlation, even if it is the highest for this image, it is very low in the whole data set. So it is not only that the experimental image vote, but the projections also vote. And we can encode this in terms of significance, and at the end give weights to the different particles. Why measuring correlation? Let's say you are looking from this direction, so the surroundings will also have very high correlation. So is there a measure that is more sensitive to small variations of the data? And there is this one, IMED. IMED is more sensitive. You see the slope here is larger than 1. So the slope here is larger than here. So it means that it is more sensitive than the cross correlation. Then doing a single angular assignment. So let's say I have to decide for a projection where it is coming from. So I don't know if it is from here or from there. So the maximum likelihood is, okay, it is coming from both places with different weights. But let's say you make the right decision in 70% of the cases. So you take the maximum in 70% of the cases. So 70% of your alignment is correct. If you allow 2 positions, then 70% of the cases in the first decision was correct, and for the 30%, you also have a 70% chance of choosing the right place. So at the end, in the final data set that is going into 3D reconstruction, only 45% of the images are correctly assigned, while with only one assignment, you have 70%. So if you want to go to very high resolution, allowing the images to be in 2 places is really not such a good idea. Then the CTF has an envelope. You should correct for the envelope before going into the 3D reconstruction. Otherwise, you are introducing some systematic bias. And you can remove all things that are not significant. So you can learn from the outside what is the distribution of noise, and then go inside and dampen those regions, for instance, this one here, things in between, that look not so different from the noise. Okay, so here are some results of this high-res reconstruction. So this is a ribosome data. This is the angular distribution coming from Reliant, and the one from high-res. So the same data give different angular coverage. This is in terms of local resolution. You see this is more blue than this one. This has a higher resolution than this one. This is a histogram. This is a Reliant. This is a high-res. So you see this looks like a low-pass filter version of this one. And the same happens with other structures. So this is beta-galactosidase. This is Reliant. This is high-res. This is a proteasome. And again, this is a low-pass filter version of this one. A virus. And some tutorial data, but you see with very few data, Reliant doesn't converge to the right structure. This one is converging to the right thing. There are some stripes here that are incorrect. And you see that in terms of resolution, the number, it is basically more or less the same. It is about 8 angstroms. So having a number, putting a number on a structure doesn't mean that your structure is good. And actually, the problem from this data set is that you have very little angular coverage, and you can never have a good structure with this data. And this is another example. I cannot tell you the protein that it is, but this has a very biased angular sampling. So most of the images are coming from one region. They are top views. And with Relion, it was totally impossible. With high-res, it worked. So making more complex workflows, I would say it pays the effort. It is more complex. You have to take decisions. It takes more time. But combining the results from different packages, I think it is a good idea. And here is the beta-galactosidase 2.2 reconstructed originally by Subramanian, and then from Relion, and then from XMIP high-res, and all these complex workflows. And we all report 2.2, so it seems to be a kind of magical number for a structure. But when you look at the details of the structure, they really look different. So just putting a number is not the whole thing. And actually, if you think of this simplification into a number, resolution is a tensor. So it's something that changes over space and changes also with directions. So if you look at in Fourier direction, in the Fourier space, there are some directions with much better resolution than in some other. So it is something that is for every point, and every direction is different. And we are summarizing all this rich information into a single number that is not so good. So yeah, I will skip this. These are some details of the high-res reconstruction. And just as a conclusion, I would say, if you pay a lot of attention to the data processing, you can get much better things. And don't use just one package. Use a lot of them. Scipion in there is very good because it allows you to test many things. It gives you consensus of many things. And I think you will have better structures. And just to finish, probably you are all aware of these projects, INEX, Instruct, Corbett, that you can have access to microscopes. So you submit your project. If it is approved, you can access the microscope for free. And also you can access to the image processing service in Madrid for free too. So and now I'm open for questions.
So thank you. Do we have questions? Judith?
Just a quick, well, thank you for this talk. It's certainly very inspirational to try all different packages. My question is, have you found any particular order of different packages to be used, for instance, in the 2D classification?
The order?
Does it matter if I start with Relion and move on to something else, or do it the other way around?
I wouldn't say so much. It depends on the order, but yeah, normally depends on, for instance, 2D classification. I normally use this screening that rejects very bad things, and then Relion is concentrating everything into a single class, into a few classes. And then the bad ones are really bad, but if you look at the images in the good ones, they are not always good. So that is my natural second step, and then CL2D from XMIP. But there are many others, so you can simply try. The idea is to make the algorithms orthogonal to each other. So you apply one step, and then the next one shouldn't have the same goal function, the same algorithm as the first one, because otherwise they are all aligned.
Hey, Tom, this one.
Thanks. I was wondering, It strikes me that Scipion can do some really handy things. One that springs to mind is looking up particles coordinates from a set of particles in, say, a class or something. Go and look at where they are in the micrograph. A lot of people have like their own hacked scripts for that. I feel like it'd be. I haven't found a tutorial for Scipion, but is a sort of revamped tutorial something you might look at producing? It would be really.
Yeah, we have a lot of tutorials in the web, and we also have a lot of videos how to do specific things, covering the tutorials too. We are giving a lot of courses, so it is also good when you have someone to talk to.
Yeah.
And yeah, so and if you have a script that are not covered in Scipion, you can easily contact us, and we see the way to put them in.
I've somehow missed it, but maybe that's my bad. But I think Scipion's a great package. Thanks for the talk.
Okay, one more at the back.
Okay. In some of your examples, you were showing cases where particles had leaked into the 3D, and then when you went back to the micrograph, they were clearly not proper particles at all. So that you can identify by visual inspection. Is it worth including a visual inspection step in this screening operation?
Yeah, I would say visual inspection is one check-in, but you should put all the monitors checks at all the points in your pipeline. So don't go blindly from the beginning to the end, applying all these steps, because this is the recipe to get the structure, but you should verify all the steps in between. Visual inspection is one of them.
Okay, I think in the interest of time, we'll move on. So if we can thank Carlos one more time.